Part 1. Island Universes. What is a galaxy, and how did we discover them? If you look up at the night sky from a dark enough place, you'll see hundreds of stars twinkling overhead. But what you're really seeing is just the tiniest glimpse of something much bigger, something so vast and full of mystery that for most of human history, we didn't even know it existed. That something is a galaxy, and the one we live in is just one of hundreds of billions. A galaxy is a massive collection of stars, gas, dust, and dark matter, all held together by gravity. Some are elegant spirals, some are giant balls of old stars, and some are chaotic and irregular in shape. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. That's just one galaxy. And until the early 20th century, most people believed it was the only one. For ancient civilizations, the Milky Way was a glowing band stretching across the sky, full of mystery. In Greek mythology, it was said to be milk spilled by the goddess Hera. The Romans kept the name Via Lactea, or Milky Road, but no one knew what it really was. Even in the 1600s, when Galileo first turned a telescope to the sky, all he could see was that the band was made up of countless faint stars. It was clear the Milky Way was huge, but still, people thought the stars we saw were all there was, that the universe was the size of our galaxy, and that we were at its center. But then came a turning point, one that would change our understanding of the universe forever. In the early 1900s, astronomers began noticing fuzzy patches in the night sky, little clouds of light that didn't look like stars. They were called nebulae, which simply means clouds in Latin. Some, like the Orion Nebula, were clearly clouds of gas, but others, like the Andromeda Nebula, were different. They had a structure, a spiral shape, something that looked almost like a pinwheel. The question was, what were they? Some astronomers believed they were just gas clouds inside the Milky Way. Others believed they might be island universes, entire galaxies of stars far beyond our own. The debate came to a head in 1920 in what became known as the Great Debate between astronomers Harlow Shapley and Heber Curtis. Shapley argued that the Milky Way was the entire universe, and everything we saw was within it. Curtis disagreed. He believed the Milky Way was just one of many galaxies, that the universe was far larger than anyone imagined. The answer arrived a few years later, thanks to one man, Edwin Hubble. Working at the Mount Wilson Observatory in California with the world's most powerful telescope, Hubble looked at the Andromeda Nebula and made a groundbreaking discovery. He found a type of star called a Cepheid variable, which changes brightness in a predictable way. By measuring how bright it appeared from Earth and knowing how bright it actually was, he could calculate its distance. The result shocked the scientific world. Andromeda was more than 2 million light-years away, far outside the Milky Way. It wasn't a gas cloud. It was a galaxy in its own right. And suddenly, everything changed. The universe was no longer a single galaxy. It was full of them. Today, we estimate that the observable universe contains over 200 billion galaxies. Some are small and faint, containing just a few million stars. Others, like giant ellipticals, can contain trillions. They come in a range of shapes, sizes, and colors. Some with elegant spiral arms, others shaped like glowing rugby balls, and some with no clear shape at all. Galaxies are not scattered randomly. They form patterns, clustering together in groups, superclusters, and vast cosmic webs that stretch across the universe. The largest structures in the cosmos are shaped by galaxies and the invisible dark matter that holds them in place. But what exactly are galaxies made of? At the most basic level, a galaxy is made of stars, vast numbers of them, many with their own planetary systems. These stars are born in clouds of gas and dust, often found in the spiral arms of galaxies like our own. As stars age and die, they create heavier elements, enriching the galaxy over time. This ongoing cycle of birth and death gives galaxies their character. Galaxies also contain nebulae, regions of gas and dust where new stars are born. And at the center of nearly every large galaxy, there is something even stranger: a supermassive black hole. These black holes can be millions or even billions of times the mass of the Sun. In some galaxies, they're quiet. In others, they blaze with energy, powering brilliant quasars visible across the universe. And there's something else. Something we can't see. Galaxies rotate. And based on how fast they spin, there should be far more gravity than the visible matter accounts for. This leads us to the conclusion that galaxies are surrounded by enormous halos of dark matter, invisible material that doesn't emit light but exerts gravitational pull. Without dark matter, galaxies couldn't hold together. In the last century, our understanding of galaxies has exploded. We've sent space telescopes like the Hubble Space Telescope to peer deep into the cosmos. The famous Hubble Deep Field image, taken by pointing a telescope at what seemed like an empty patch of sky, revealed thousands of galaxies in a single tiny frame. Every speck of light in that image wasn't a star. It was an entire galaxy. These discoveries have forced us to rethink our place in the universe. The Earth orbits an average star. That star sits in a spiral arm of a galaxy, not at the center, but in the suburbs, and that galaxy is just one among billions. It's humbling, but it's also thrilling, because galaxies are the homes of stars, planets, and possibly life. And the story of how galaxies formed, evolved, collided, and changed over time is the story of the universe itself. From the ancient belief in a single fixed sky to the realization that we live in a vast sea of galaxies, the journey has been one of curiosity, courage, and relentless exploration. Each galaxy is a universe of its own, an island of stars adrift in a cosmic ocean. And we, on our tiny pale blue dot, have begun to chart that ocean, to map its structure, to study its origins, and to understand how galaxies like our own came to be. In the next part, we'll go back in time and explore how the first galaxies formed, how from the ashes of the Big Bang, matter gathered into clumps, ignited into stars, and lit up the universe for the first time. Part 2. Building the Starscapes. How do galaxies form and grow over time? When we gaze at galaxies through telescopes today, we see elegant spirals, massive ellipticals, and glowing clusters of stars. But these majestic cosmic cities weren't always so grand. They started from much humbler beginnings. Small ripples in the fabric of space, tiny clumps of matter drawn together by gravity in the wake of the Big Bang. To understand how galaxies formed and evolved into the structures we see today, we have to go back nearly 14 billion years, to a time when the universe was still dark. After the Big Bang, the universe expanded and cooled. Matter was spread out evenly, but not perfectly. In the earliest fractions of a second, quantum fluctuations, minuscule differences in density, were stretched to cosmic scales by inflation. These became the seeds of all future structure. We can still see them today, etched into the cosmic microwave background. Tiny hot and cold spots that show where matter was just slightly more or less dense. Over the next few 100 million years, gravity did its slow, patient work. Regions with slightly more matter pulled in more material from their surroundings, growing denser and hotter. These were the first building blocks of structure, the earliest dark matter halos. Though we can't see dark matter directly, we know it was essential. Its gravitational pull helped gather gas into these halos, forming the frameworks where galaxies would be born. Inside these halos, clouds of hydrogen and helium gas began to collapse under their own weight. As they fell inward, the gas compressed and heated up. Eventually, deep in the centers of these clouds, the conditions became just right for something extraordinary to happen. The first stars ignited. This era, known as cosmic dawn, marked the universe's transition from darkness to light. These first stars, called population 3 stars, were likely very different from the stars we see today. They were massive, hot, and short-lived, burning through their fuel in just a few million years. Because the early universe had no heavy elements, these stars were made almost entirely of hydrogen and helium. But through nuclear fusion, they began forging heavier elements in their cores. When they died in powerful supernovae, they scattered those elements into space, enriching the gas and preparing the way for future generations of stars and planets. The explosions of these first stars also helped shape their environments, pushing gas into new regions and triggering the birth of more stars. Over time, small groups of stars and gas came together, merging into larger and more complex systems. These were the proto-galaxies, the first true galaxies in the universe. But galaxies didn't grow in isolation. The early universe was a crowded place, and gravitational attraction pulled galaxies toward each other. Many of the first galaxies collided and merged, combining their stars and gas. These mergers were violent but crucial. They helped galaxies grow larger and sparked waves of star formation, lighting up the cosmos with new energy. Some galaxies grew faster than others, depending on their environment and how much dark matter surrounded them. In regions with more matter, galaxies formed earlier and became bigger. In emptier areas, galaxies evolved more slowly. This led to the large-scale structure of the universe, a cosmic web of galaxies and clusters stretching across space. The galaxies we see today are the result of billions of years of this complex dance, a mix of collapse, formation, collision, and growth. Spiral galaxies like our own Milky Way formed when gas settled into a rotating disk, where stars could form in orderly patterns. Elliptical galaxies often formed from the mergers of spirals, their stars thrown into random orbits, creating a more rounded shape. But galaxy formation didn't stop in the early universe. It's still happening today. New galaxies continue to form from clouds of gas and dust. Existing galaxies continue to collide and merge. The Milky Way, for example, is currently absorbing smaller galaxies around it, and in about 4 billion years it will collide with the nearby Andromeda galaxy to form a new, larger galaxy. The growth of galaxies isn't just about adding stars, it also involves the balance between gas coming in and energy going out. Gas fuels star formation, but it can also be pushed out by intense radiation, supernova explosions, and even jets from supermassive black holes. These feedback processes regulate how fast galaxies grow, shaping their appearance and their ability to form new stars. As galaxies grow, they change. Some spiral galaxies become more structured, with well-defined arms and central bars. Others become more elliptical, especially after big mergers. Some run out of gas and stop forming stars altogether. These are called quenched galaxies, and they gradually fade into a quieter, redder state as their older stars age and die. Scientists use powerful telescopes like the James Webb Space Telescope to peer back in time and watch galaxies at different stages of their lives. Because light from distant galaxies takes billions of years to reach us, we can see them as they were when the universe was young. These deep observations allow us to build a timeline, a cosmic history book, showing how galaxies changed over billions of years. Computer simulations also play a key role. By starting with the conditions of the early universe and applying the laws of physics, scientists can model how galaxies form and evolve over time. These simulations, like Illustris or Eagle, produce virtual universes that look strikingly similar to what we observe, confirming that our understanding of galaxy formation is on the right track. And yet there are still many mysteries. For instance, why do some galaxies stop forming stars while others continue? How exactly does dark matter shape galactic structure? What causes the formation of different shapes? Spirals, ellipticals, or irregulars? And how do the central black holes influence the life of a galaxy? The answers are still emerging. But what we do know is this: galaxies are not static objects. They are living, evolving systems, shaped by the interplay of matter, energy, and time. They are born from gravity and gas, grow through mergers and star formation, and are sculpted by feedback and environment. The story of galaxy formation is the story of cosmic creativity, how the universe took the raw materials of the Big Bang and slowly built the magnificent structures we see today. From tiny fluctuations to vast stellar cities, the process has taken billions of years, and it's still unfolding. In the next part, we'll explore the many faces of these galaxies, why they take such different forms, and what their shapes tell us about their pasts. Part 3. The Galactic Zoo. Why do galaxies come in so many shapes and sizes? When you picture a galaxy, you might think of a grand spiral, its arms swirling outward like a cosmic pinwheel. That's not a bad mental image. After all, the Milky Way itself is a spiral galaxy. But galaxies come in many shapes and sizes, some elegant, others chaotic, and each type holds clues about a galaxy's age, history, and environment. This diverse collection of galactic forms is often called the Galactic Zoo. It's not just a nickname. It reflects how scientists classify galaxies based on what they look like, and how those appearances relate to deeper cosmic truths. Let's begin with the most familiar kind, spiral galaxies. These are the cosmic beauties of the universe. They have a flat, rotating disk of stars, with graceful arms that wind outward from a central bulge. The arms are not fixed structures. They're more like waves of higher density that pass through the disk, compressing gas and triggering star formation as they go. That's why spiral arms are often rich in bright, young blue stars. The Milky Way is a barred spiral galaxy, which means it has a bar-shaped region of stars stretching through its central bulge. This bar acts like a traffic system, helping to funnel gas inward toward the center, where new stars can form, or where the galaxy's central black hole might be fed. Spiral galaxies are typically rich in gas and dust, the raw ingredients needed to make new stars. That's why they tend to be sites of ongoing star formation. Most spirals are found in relatively low-density environments, where they can evolve peacefully without frequent collisions. But not all galaxies are this orderly. Some galaxies have no clear shape at all. These are irregular galaxies, and they live up to their name. They look messy, asymmetrical, and scattered. Irregular galaxies often form when a galaxy is disturbed, perhaps by a collision or a close gravitational encounter with another galaxy. Their structure has been jumbled by these interactions, leaving behind a chaotic mix of stars and gas. Irregular galaxies are usually smaller than spirals and ellipticals. They often contain a lot of gas and ongoing star formation, sometimes triggered by the very collisions that disturb their shape in the first place. The Large Magellanic Cloud, one of our Milky Way's satellite galaxies, is a classic example of an irregular galaxy. Then there are the giants of the galaxy world, the elliptical galaxies. These are round or oval in shape, like stretched-out footballs or eggs. They don't have spiral arms or much structure at all. Instead, their stars are distributed more evenly in all directions, orbiting the center in complex, three-dimensional patterns. Elliptical galaxies come in many sizes, from small dwarf ellipticals to massive, bloated galaxies that can contain trillions of stars. Unlike spirals, they tend to have little gas or dust, and they're not forming many new stars. Most of their stars are old, red, and low mass, signs of a galaxy that's settled into quiet retirement. How do elliptical galaxies form? One leading idea is that they result from galactic mergers. When two spiral galaxies collide, the violent interaction can scatter stars into random orbits, destroying the spiral structure and creating a more rounded shape. Over time, as star formation slows down and the gas is used up or pushed out, the galaxy becomes more passive, more elliptical. So in many ways, the shape of a galaxy is a record of its life story. Spirals are often younger or less disturbed, still rich in gas and forming stars. Ellipticals are older, quieter, and shaped by violent events in the past. Irregulars are in the middle of the chaos, reshaped by encounters or instability. There's another important class, dwarf galaxies. These are small galaxies with only a few million to a few billion stars, tiny compared to the Milky Way. Dwarf galaxies are thought to be the building blocks of larger galaxies, like cosmic bricks, that were assembled over billions of years. Most galaxies in the universe are actually dwarfs. They often orbit larger galaxies as satellites, and they can be easily influenced by their neighbors. Some get stripped of their gas, or even torn apart by gravitational forces. But others survive and remain active, continuing to form stars or drift alone in quieter parts of space. To organize this diversity, astronomers often use a system known as the Hubble sequence, or the Hubble tuning fork. This diagram, developed by Edwin Hubble in the 1920s, arranges galaxies by shape, ellipticals on one side, spirals on the other, and lenticular galaxies, a kind of transitional form in the middle. Lenticular galaxies, or S0 galaxies, look like spirals without the arms. They have a disk and a bulge, but little gas and no significant star formation. Some scientists think they're spirals that have aged and faded, or ellipticals that flattened out in certain environments. They occupy the middle ground in the Galactic Zoo, quiet and orderly, but lacking the drama of spirals or the firepower of collisions. But shape is just one piece of the puzzle. Galaxies also differ in color, brightness, and mass. These properties tell us about the ages of their stars, their star formation rates, and their environments. Galaxies with lots of young stars tend to be bluer and brighter in ultraviolet light. Older galaxies are redder and glow more in infrared. Galaxies don't just exist on their own. They form groups and clusters bound by gravity. Our Milky Way is part of the local group, a small gathering of a few dozen galaxies. Larger clusters, like the Virgo cluster, contain hundreds or even thousands of galaxies. In dense environments, galaxies interact more often, influencing their shapes and star-forming activity. There's even a connection between a galaxy's shape and the supermassive black hole at its center. Spirals tend to have smaller black holes, while ellipticals often host the biggest ones. Some of these central black holes are quiet, while others power intense jets of energy, turning the galaxy into an active galactic nucleus or a quasar. And as telescopes improve, astronomers continue to find galaxies that defy classification. Galaxies with double cores, ring structures, or tails of stars stretching across space. The zoo keeps growing, and each new discovery challenges our understanding. So why do galaxies come in so many shapes and sizes? Because their lives are long, dynamic, and full of events. Their shapes are shaped by motion, gravity, time, and environment. Some are born in calm regions and grow slowly. Others are forged in chaos, torn apart, and reborn through collision. In this galactic zoo, each shape tells a story, not just about what the galaxy looks like now, but about how it lived, what it's been through, and what it may become. In the next part, we'll come home to our own galaxy, the Milky Way, and take a closer look at its structure, its hidden parts, and our place within it. Part 4. The Milky Way Revealed. What do we know about our home galaxy? We live inside a galaxy so vast, so full of stars, and so complex that it has taken centuries just to begin to understand it. The Milky Way galaxy is our cosmic home, the island of stars, dust, gas, and dark matter that cradles our solar system and billions of others. Though we can't see it from the outside, scientists have spent decades mapping it from within, uncovering its structure, its history, and our place within this grand, spiral-shaped city of stars. Let's begin with what we can see. On a clear, dark night, far from city lights, the Milky Way appears as a faint, glowing band stretching across the sky. Ancient cultures around the world gave it names: the River of Heaven in China, the Backbone of Night in Africa, and the Pathway of Souls in parts of the Americas. To early astronomers, it seemed like a mysterious smear of light. But Galileo, using one of the first telescopes, discovered that this glow was made of countless faint stars, packed so densely that their light blended into a misty stream. But how big is the Milky Way, and what shape does it really have? The Milky Way is a barred spiral galaxy, a type of galaxy with a central bar-shaped region of stars and a flat, rotating disk where spiral arms extend outward. The entire galaxy is roughly 100,000 light-years across and a few thousand light-years thick. It's shaped like a pancake with a bulge in the middle, and our solar system sits about 27,000 light-years from the center, in one of the spiral arms known as the Orion Arm. Because we live inside the Milky Way, we can't take a picture of it the way we can photograph distant galaxies. Instead, we've had to build a model of its structure using indirect evidence, mapping the positions and motions of stars, studying the distribution of gas and dust, and using radio waves, infrared light, and other forms of radiation that can penetrate the dusty disk. The Milky Way has several key components. At the center is the galactic bulge, a thick, football-shaped region packed with older stars. This bulge is surrounded by the bar, a stretched-out stream of stars that helps funnel gas inward. From the ends of the bar, the spiral arms extend outward, winding through the flat disk like giant rivers of stars, gas, and dust. These spiral arms are not solid structures. They're more like traffic jams in space, regions where matter bunches up as it orbits the center. As gas clouds move through these arms, they get compressed, triggering the formation of new stars. That's why spiral arms are often lit with bright young stars and glowing nebulae. Above and below the disk is the galactic halo, a roughly spherical region filled with scattered stars, ancient star clusters, and vast amounts of dark matter. Most of the Milky Way's mass is invisible, made of this dark matter that doesn't emit or reflect light, but exerts gravitational pull. Without it, the galaxy wouldn't hold together. Orbiting within this halo are dozens of satellite galaxies, including the large and small Magellanic Clouds, which are visible from the southern hemisphere. These smaller galaxies interact with the Milky Way, sometimes getting stretched, disrupted, or slowly absorbed. Over billions of years, the Milky Way has grown by cannibalizing many of its neighbors, and it's still doing so today. At the very center of the galaxy lies something truly extraordinary, a supermassive black hole called Sagittarius A Tez, pronounced A-star. It has a mass about 4 million times that of the Sun, and it sits quietly, for now, at the heart of the Milky Way. We can't see it directly, but we know it's there because of how nearby stars orbit at incredible speeds, pulled by its immense gravity. In other galaxies, similar black holes can become active, devouring matter and unleashing powerful jets of energy. The stars in the Milky Way come in many generations. Some are relatively young, just a few million years old, still surrounded by the gas and dust they were born from. Others are ancient, more than 10 billion years old, relics from the galaxy's earliest days. These oldest stars are often found in globular clusters, dense, spherical groups of stars that orbit the galaxy in its halo. Studying these stars helps scientists piece together the Milky Way's formation history. So how did our galaxy form? Current models suggest that the Milky Way began as small clumps of gas and dark matter in the early universe. Over time, these clumps merged, grew, and collected more material. Smaller galaxies were pulled in and added to the mix. The spiral disk formed as gas settled into a rotating plane, and the bulge likely grew from early starbursts or mergers. Even today, the Milky Way is still growing. It's in the process of consuming several dwarf galaxies, including the Sagittarius dwarf galaxy, which is currently being stretched and torn apart as it passes through the Milky Way's disk. And the biggest future event is still to come. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor. The two galaxies are on a slow-motion collision course, drawn together by gravity. When they finally meet, their shapes will be torn and stretched. Stars will not crash into each other. Space is too vast. But their orbits will be rearranged, and new waves of star formation will be triggered. Eventually, the two galaxies will merge into one larger elliptical galaxy, often nicknamed Milkomeda. Living inside a galaxy means we can only ever see parts of it, like trying to understand a forest while standing under the trees. But thanks to centuries of observation, modeling, and exploration, we've built a detailed picture of the Milky Way, its size, shape, history, and hidden structure. It's easy to forget that everything we know, every person, every tree, every building, every planet, exists inside just one galaxy. Yet this one galaxy contains hundreds of billions of stars, thousands of star clusters, and vast amounts of gas, dust, and dark matter. It is a dynamic, evolving system, not a static background to the night sky, but a living, breathing structure full of motion, birth, and transformation. And perhaps most importantly, the Milky Way reminds us that we are part of something vast. Our solar system is just one tiny thread in a much larger tapestry, a single orbiting speck in a disk of light that itself is only one galaxy among billions. In the next part, we'll turn from quiet spiral arms to cosmic collisions. What happens when galaxies crash into each other? How do these enormous events reshape the universe? The story of galaxies in collision is one of violence, transformation, and cosmic renewal. Part 5. Galaxies in Collision. What happens when galaxies crash into each other? The universe may seem like a quiet, peaceful place when we look up at the stars, but over cosmic time, it's anything but still. Galaxies, those grand cities of stars, don't simply float in space forever, untouched. They move, they grow, and sometimes they collide. These encounters aren't quick, and they don't happen often in a human lifetime, but over millions and billions of years, galactic collisions are common and spectacular. At first, it might seem strange that such massive objects, each containing billions or even trillions of stars, could crash into each other. But in the vast reaches of the cosmos, gravity is always at work, pulling galaxies toward one another. Galaxies are not isolated. They exist in groups and clusters bound by gravity. And within those clusters, they drift, orbit, and eventually, sometimes inevitably, come too close. Now, when we say galaxies collide, it's important to understand what that actually means. A galaxy is mostly empty space. Even though it contains an enormous number of stars, the distances between those stars are vast. If two galaxies collide, it's incredibly unlikely that any individual stars will smash into each other. Instead, the collision is more like a gravitational storm, a slow-motion warping, stretching, and stirring of both galaxies' contents. Imagine two clouds passing through each other, but each cloud is made of stars, gas, dust, and dark matter. As they approach, their mutual gravity begins to pull and distort them. Tidal forces, the same kind that affect Earth's oceans, tear at the galaxy's shapes, stretching them into long tails or plumes. Gas clouds inside the galaxies crash into one another, compressing and heating up. This process often triggers bursts of star formation, lighting up the galaxies with new hot stars. These are known as starburst galaxies, glowing reminders that even in chaos, creation thrives. One of the best-known examples of this is the Antennae galaxies, located about 60 million light-years away. These two spiral galaxies are in the middle of a collision, their arms tangled, long tails stretching into space, and regions glowing with intense star formation. They offer a glimpse of what's to come for our own galaxy. Because, yes, the Milky Way is on a collision course of its own. In about 4 billion years, the Milky Way will merge with the Andromeda Galaxy, our nearest large neighbor. The two are currently about 2.5 million light-years apart, but they're moving toward each other at around 110 kilometers per second. When they finally meet, their shapes will be torn apart, spiral arms flung into space, and huge amounts of gas and dust will collide, triggering new generations of stars. Over the course of this epic event, lasting billions of years, the two galaxies will pass through each other multiple times. Their central black holes may spiral inward and eventually merge. And in the end, the two spirals will settle into a new form, likely a large, elliptical galaxy, sometimes referred to as Milkomeda. While this might sound alarming, there's no need for worry. The vast emptiness between stars means that even during this titanic clash, our solar system will almost certainly survive unscathed. The night sky will change dramatically, with new stars, arcs of glowing dust, and the luminous core of Andromeda growing larger with time. But Earth itself is unlikely to be harmed by the collision. In fact, galactic collisions are essential to the evolution of the universe. In the early cosmos, galaxies were smaller and more irregular. Through collisions and mergers, they grew. Spiral galaxies sometimes merged to form ellipticals, and tiny dwarf galaxies were absorbed by larger ones. These interactions helped galaxies become more massive, build new stars, and evolve into the diverse forms we see today. Not all encounters are equal. Sometimes a large galaxy absorbs a much smaller one, a process known as galactic cannibalism. The larger galaxy pulls the smaller one apart, stealing its stars and gas. The Milky Way is doing this right now to several small galaxies, including the Sagittarius dwarf galaxy, which is being stretched into a stream of stars that wraps around our own. In denser regions of the universe, like galaxy clusters, collisions are more frequent and complex. Galaxies may pass through hot gas, lose their own gas supply, or be flung apart by gravitational slingshots. In these environments, we often find large elliptical galaxies that have grown by merging with many smaller galaxies over time. Sometimes, a collision can even cause a galaxy to lose its ability to form new stars. If the gas is stripped away or used up in a starburst, the galaxy may settle into a quieter phase. Over time, its bright young stars burn out, and it becomes a red dormant galaxy, a quiet graveyard of aging stars. Collisions also affect the dark matter halos that surround galaxies. These invisible halos overlap and combine, influencing the way galaxies move and behave after a merger. Studying these halos helps scientists understand the properties of dark matter and how it interacts or doesn't interact during cosmic collisions. Galactic mergers can also awaken the supermassive black holes at the centers of galaxies. As gas funnels toward the center during a merger, it can feed the black hole, causing it to flare to life as an active galactic nucleus. In extreme cases, the galaxy becomes a quasar, blazing with energy as matter spirals into the central black hole at nearly the speed of light. Simulations of galaxy mergers, powered by supercomputers, allow scientists to visualize how these encounters unfold over time. Programs like Illustrious and Eagle show how galaxies grow through mergers, transform in shape, and influence their surroundings. These models, combined with telescope observations, give us a clearer picture of how the universe builds its grand structures. What's truly remarkable is how much beauty comes from these cosmic collisions. They are not simply destructive, they're part of a larger pattern, a cosmic life cycle in which galaxies grow, change, and give birth to new generations of stars. Without collisions, many galaxies would remain small and faint. The grand, glowing spirals and enormous ellipticals we see in the night sky are, in many cases, the result of ancient encounters. So when you look at a picture of two galaxies locked in a slow-motion dance, remember that you're not just seeing destruction, you're seeing transformation. The universe is not static. It evolves. And galactic collisions are one of the main engines driving that evolution. In the next part, we'll zoom out even farther, beyond individual galaxies and collisions, to see how galaxies are arranged on the largest scales. What do galaxy clusters, superclusters, and the cosmic web tell us about the universe's structure? Let's step into the vast framework that holds the galaxies themselves, the web of the cosmos. Part 6. The Web of the Cosmos. How are galaxies arranged across the universe? When we look at a single galaxy, like the Milky Way or Andromeda, we see an immense structure filled with stars, planets, gas, and dark matter. But galaxies themselves are not scattered randomly across space. They are part of something even larger, a grand structure that spans the entire observable universe. This structure is often called the cosmic web, and it is one of the most awe-inspiring discoveries in all of astronomy. To the human eye, the universe can feel empty. Stars seem far apart. Even galaxies are usually separated by vast stretches of blackness. But with powerful telescopes and decades of data, astronomers have uncovered a hidden pattern. When they map the positions of hundreds of thousands of galaxies across the sky, a picture begins to emerge, a pattern of filaments, clusters, and enormous voids, woven together like threads in a cosmic fabric. This is the large-scale structure of the universe, and it's far from uniform. Galaxies are not scattered like grains of sand in a box. They follow a specific distribution, forming strands and nodes that stretch across billions of light years. At the intersections of these strands, galaxies gather in groups and clusters. These clusters are like the cities of the universe, dense regions full of galaxies bound together by gravity. Between the strands lie vast cosmic voids, regions of space that contain very few galaxies at all. So, how did this cosmic web form? To answer that, we have to go back to the early universe, shortly after the Big Bang. At that time, matter and energy were spread out almost evenly, but not perfectly. There were tiny differences in density, small fluctuations that we can still see today in the cosmic microwave background. These fluctuations were the seeds of structure. Over time, gravity pulled matter into the slightly denser regions, and the denser they became, the more matter they attracted. As the universe expanded and cooled, these dense areas collapsed into the first dark matter halos, pulling in gas and forming the earliest galaxies. But the dark matter itself, which makes up most of the mass in the universe, also followed this pattern. It clumped into filaments and sheets, creating a web-like scaffold on which galaxies and clusters could grow. In fact, galaxies are just the visible tips of this dark matter framework. Where we see clusters of galaxies, we know there must be vast halos of dark matter holding them together. And where there are few or no galaxies, there is less dark matter, or at least, it is more spread out. The best evidence for this web-like structure comes from massive surveys of the sky, such as the Sloan Digital Sky Survey, which has mapped the positions of over 1 million galaxies. These surveys show long chains of galaxies stretching across space, like cosmic highways, and enormous regions of near-nothingness in between. Some of these voids are hundreds of millions of light-years across. One famous example of this pattern is the Butte's void, an enormous bubble of nearly empty space roughly 330 million light-years in diameter. By contrast, in regions like the Coma cluster, we find thousands of galaxies packed closely together, each one a universe of stars. But clusters are more than just galaxy collections. They are environments filled with hot gas, strong gravitational fields, and interactions that shape the galaxies inside them. The gas between galaxies in a cluster is so hot it emits X-rays, which we can detect with space-based telescopes. The gravity of a cluster is so strong it can bend light, a phenomenon known as gravitational lensing, allowing us to map the invisible dark matter within. Clusters are grouped into even larger structures called superclusters. Our own Milky Way is part of a smaller galaxy group called the Local Group, which includes Andromeda and about 50 smaller galaxies. The Local Group itself is part of the Laniakea supercluster, a vast region of space containing over 100,000 galaxies. The name Laniakea means immense heaven in Hawaiian, a fitting description for our cosmic neighborhood. All of this fits into an even bigger picture, the cosmic web, a term that captures the entire large-scale structure of the universe. This web was first predicted by computer simulations in the 1980s and has since been confirmed by observations. It is the result of billions of years of gravitational growth, shaped by the initial conditions of the Big Bang, and driven by the hidden scaffolding of dark matter. The cosmic web isn't static. Galaxies move along its filaments, falling into clusters, merging and changing. Over time, clusters grow larger, pulling in more galaxies from the surrounding filaments. Void regions expand as matter flows away into denser areas. It's a slow but ongoing process. The universe is still building itself. Studying the large-scale structure of the universe is not just about mapping where galaxies are. It helps us understand fundamental questions about the universe itself. How much dark matter and dark energy are there? What are the properties of gravity on the largest scales? How did galaxies grow and evolve within their cosmic environments? Modern instruments like the Euclid Space Telescope and the Dark Energy Survey are helping astronomers map the cosmic web in greater detail than ever before. By looking at the distribution of galaxies, the bending of light, and the motion of gas and stars, scientists can test theories about dark matter, dark energy, and the nature of the universe itself. The web of the cosmos also reveals something profound. Our galaxy, our solar system, even our own planet, all of it exists not in isolation, but as part of a vast network of structures stretching across the universe. We are a small thread in a much larger fabric, shaped by forces that have been in motion since the universe began. From the glowing strands of galaxies to the deep, dark voids in between, the cosmic web is a masterpiece of natural design. It is a map of gravity, time, and matter, a reminder that the universe is not only full of beauty but also full of structure and meaning on every scale. In the final part of this series, we'll ask one last question. What happens to galaxies in the end? Do they live forever, or can a galaxy die? We'll explore the life cycle of galaxies, how they age, fade, and sometimes vanish altogether. Part 7. Life and Death of Galaxies. Can a galaxy die? And what happens then? Galaxies are some of the most breathtaking structures in the cosmos. Grand spirals brimming with stars, elliptical giants glowing with ancient light, and chaotic irregulars bursting with newborn suns. They form, grow, collide, and evolve. But like all things in nature, galaxies also have a life cycle. They are born, they change, and eventually, they grow quiet. Some even fade away. So what does it mean for a galaxy to live or die? And what happens in the final chapters of a galaxy's story? Let's begin with what keeps a galaxy alive. In astronomy, a living galaxy is one that is actively forming new stars. Star formation is the heartbeat of a galaxy. It takes place in massive clouds of cold gas, mostly hydrogen, that collapse under gravity, ignite nuclear fusion, and give birth to glowing stars. As long as a galaxy has enough gas to fuel this process, it can keep producing new generations of stars. But gas is not infinite. Over time, galaxies use up their fuel. The cold gas gets turned into stars, or is blown away by powerful winds from supernovae, black holes, or bursts of radiation. Once the gas supply runs low, star formation slows, and eventually, it stops. At that point, the galaxy begins to grow quiet. This is what astronomers call a quenched galaxy, one where the star-making machinery has shut down. A galaxy that is no longer forming stars still contains billions or trillions of stars, but without new stars to replenish the population, the galaxy starts to fade. Its youngest, brightest stars burn out quickly, leaving behind older, redder stars. Over billions of years, the galaxy becomes dimmer and redder, like a city where no new lights are being turned on. This process of galactic aging is visible in the colors of galaxies. Star-forming galaxies are often blue and bright, filled with hot young stars. Quenched galaxies, by contrast, are redder and dimmer. This difference gives rise to the so-called galaxy color sequence, where galaxies fall into a blue cloud, a red sequence, or somewhere in between, depending on their level of activity. But how does a galaxy lose its ability to form stars in the first place? There are several ways this can happen. One is through internal exhaustion. The galaxy simply runs out of cold gas, but more dramatic processes can also play a role. For example, when two galaxies collide and merge, The resulting burst of star formation can use up the remaining gas in a cosmic fireworks show. Afterward, the merged galaxy may be left with no fuel, entering a quiet phase. Another factor is the environment. Galaxies in dense clusters often suffer from processes that remove or heat up their gas. One such process is ram pressure stripping, where a galaxy moving through a cluster's hot gas has its own gas blown away like leaves in the wind. Without gas, star formation halts. In some cases, supermassive black holes at the centers of galaxies can influence their fate. When these black holes become active, feeding on gas and flaring with energy, they can release powerful jets and winds that push gas out of the galaxy or heat it up so it can't form stars. This feedback process can effectively shut down star formation and steer the galaxy into a quieter future. As time goes on, a galaxy that no longer forms stars will continue to change. The brightest stars will die first, exploding as supernovae or fading into white dwarfs. Medium-mass stars like our Sun will swell into red giants and eventually shed their outer layers, leaving behind planetary nebulae and faint stellar cores. The galaxy becomes increasingly filled with older, cooler stars. But what about the very end? In the far future, tens or hundreds of billions of years from now, if the universe continues expanding, galaxies will drift farther apart. New star formation will cease in most places. Over trillions of years, existing stars will age and die. The universe may become a darker, colder place, filled with dead stars, black holes, and drifting remnants. This idea is known as the heat death of the universe, where everything reaches a state of maximum entropy, and no usable energy remains to power anything new. But even before that, galaxies will continue their long, slow evolution. Some will merge into larger systems, others may be torn apart by gravitational interactions. The Milky Way, for example, is expected to merge with Andromeda to form a large elliptical galaxy. Over time, many smaller galaxies will be absorbed into larger ones, reducing the overall number of individual galaxies. This process of merging and quenching means that elliptical galaxies, often the result of many mergers, may represent the retirement homes of the universe. They are large, massive, and red, filled with old stars and little new activity. They are not dead in the sense of disappearing, but their era of star-making is over. Still, even in a quiet galaxy, there can be occasional sparks of change. A fresh inflow of gas, perhaps from a passing galaxy, could reignite star formation. A collision with a smaller galaxy could stir things up. So while many galaxies follow a general pattern of birth, growth, and quiet aging, the story isn't always the same. The universe is full of surprises. There's also a chance that the universe might not end in a slow fade. Some cosmological models propose alternatives. In a big crunch, the universe could reverse its expansion and collapse back in on itself, possibly leading to a new Big Bang. In a big rip, the expansion could accelerate so much that galaxies, stars, planets, and even atoms are torn apart. And in cyclic models, the universe could go through endless cycles of expansion and collapse, with each cycle creating new galaxies all over again. But for now, what we observe is a universe that is expanding, evolving, and gradually quieting down. Galaxies are still forming stars, but many are already past their prime. The cosmic fireworks of the early universe have dimmed, and a quieter era has begun. So, can a galaxy die? In a sense, yes, though perhaps it's more accurate to say that galaxies retire. They burn through their youthful energy, settle into quieter shapes, and slowly fade into the background of the cosmos. Their stars continue to shine for billions of years, but the galaxy itself becomes a still, ancient monument to a more active time. Yet even in these quiet galaxies we find beauty, the soft red glow of aging stars, the elliptical sweep of ancient mergers, the silent presence of a massive black hole at the core. Galaxies live long lives, shaped by gravity, time, and motion, and each one, in its own way, tells the story of the universe that gave birth to it. From their fiery births to their quiet twilights, galaxies are not just structures in space. They are the storytellers of the cosmos, the glowing archives of matter, light, and time.